Hi, I'm Matthias Beck. I'm one of the authors of Computing the Continuous Discretely, and in this video we will talk about the two major reciprocity theorems in Ehrhart theory, namely Stanley Reciprocity and Ehrhart-Macdonald reciprocity. A combinatorial reciprocity theorem gives a relation between two combinatorial functions, where in one function we replace the variable either by its negative or by its reciprocal. And Stanley reciprocity is an example of the latter. In preparation, I will show you a simplicial version of Stanley reciprocity here. We have seen if we take a simplicial rational cone and shift it by a real vector, then the integer point transform evaluates to a rational function. And so this preparation result for Stanley reciprocity is about the situation where we have a rational simplicial cone where we shift it by some vector v such that the boundary of the shifted cone contains no integer point. We'll do that for both the shifted cone and the cone shifted by negative v. And so here you see a reciprocity theorem relating the two integer point transforms. In one of them, we plug in the reciprocals of the variables, and then we, up to a sign, get the other integer point transform. I want to stress that this is an identity of rational functions. This is not an identity of formal power series. And we'll have a little bit more to say about this in a moment. Let me first give an idea of how this theorem follows. Like we saw in chapter 3, we will first form the fundamental parallelepiped corresponding to this cone. And if you think about this for a moment, the fact that the shifted cone contains no integer point on the boundary implies that the shifted fundamental parallelepiped has the same property. Again, there's no integer points on its boundary. And so this means we might as well, in this case, take an open fundamental parallelepiped, which we again call pi. And by now you know how to compute integer point transforms. So in both cases, either shifting by v or by negative v, we will get a rational function with the fundamental parallelepipeds shifted by the same kind of vector. And then in the denominator we have products of 1 minus z to each generator. And now the geometry behind this reciprocity theorem on this page is this relation. There is a, if you want, elementary geometric relation between the parallelepiped pi shifted by v and the one shifted by negative v. And this in turn means that there's a relation between the integer point transform of the numerator on the left and the integer point transform on the right. The details of how this plays out is described in section 4.2. I do want to point out the place in the proof where you can see that this is an identity of rational functions. This is essentially the last step in the proof where we plug in reciprocals in one of the generating functions. And over here, going from here to the next line, you can see the geometric relation between the two shifted versions of pi translated into generating functions. So up to this point, we've really just done geometry. But now, starting with this step over here, we're doing algebra of rational functions. And it is this algebra that, at the end of the day, gives you the other integer point transform. But I want to stress one more time that the relation that's at the heart of this theorem over here is a relation of rational functions. Okay, now let me give you just a brief idea of how this theorem helps us prove Stanley's reciprocity theorems for rational cones. The setting is the same that we have in chapter 3. We have a cone, apex at the origin, and I will triangulate this cone. And just for ease of my pictures, let me assume that I have just two simplicial cones in this triangulation. I will assume that my original cone, let me call this K, is a rational cone. So that means I can triangulate it into simplicial rational cones. And now I will do the following. I will translate this whole picture by a real vector v in such a way that, number one, I will lose all the points on the boundary of K. That really means I'm going to capture the integer point transform of the interior of the cone. But I will also lose integer points on the boundaries of the simplicial cones in the triangulation. So in this case, I might do a shift like that. Yeah, so by shift, I literally mean I'm shifting now the big cone and all the individual cones by this vector v down here. Yeah, so let me go back and invite you to convince yourselves that my shift lost precisely the integer points on the boundary of K. And in addition, I shifted in such a way that any boundary hyperplane of one of my smaller cones, again, does not contain any integer lattice points. Number one, this means I'm now ready to use the initial theorem for simplicial cones with no points on the boundary. I have a reciprocity theorem now for each individual simplicial cone. But number two, this reciprocity theorem will, on the other side, get me a negative v plus each cone. And I claim if you do that, yeah, so now here is negative v, we will again have no integer points on any hyperplane bounding any of my cones. But now the integer point transform of the big cone, I claim, is equal to the integer point transform of the original cone. Let me convince you at least in this picture again. So here is the shifted cone by negative v, and here was the original cone. And I hope you can see with this shift, I do not lose nor gain any integer point in K. If you now put all these ingredients together and use the initial reciprocity theorem for simplicial cones, you will get Stanley's reciprocity theorem, which says if you have a rational cone, the origin is apex, then the integer point transform of K and the integer point transform of the interior of K are related in this fashion where you plug in reciprocals of the variables in one side, and up to a sign, you will get the integer point transform on the other side. Just like theorem 4.2, I want to stress that this is a relation of rational functions. So maybe the best way to phrase this theorem is to say, let's look at the integer point transform of K, the integer point transform of K interior. We'll write down the rational function version in each case. Then these two rational functions have a relation and is given by this equation here. There's quite a quick translation of Stanley reciprocity into a reciprocity theorem for Ehrhart series. Let me remind you that for a lattice polytope or a rational polytope, we define the Ehrhart series as the generating function of the Ehrhart polynomial or quasi-polynomial, where we appended this generating function with the constant term 1, and in chapter 3 we sort of explained where this comes from. I want to do the same thing for the interior of the polytope, so this is this p circle. Here I'm starting my generating function at t equals 1, no constant term, and I invite you to think about why this makes sense. If you think about an Ehrhart series as coming from the cone over the polytope, what that means is that the Ehrhart series is really a special evaluation of the integer point transform of this cone. On the open side for the interior of the polytope, that comes then from the integer point transform of the open cone. And while on the closed side, this 1 here came from the origin in the cone, On the open side, there is no point of height 0. So this is a long-winded motivation for the definition that you see on the right. If we now apply Stanley reciprocity to the integer point transforms of the cone over P and its interior, you will get in 2 lines the theorem that you see on this page, namely that the rational functions representing the Ehrhart series of P and that of P interior are related through this equation. And the sign that you have to correct by comes from the fact that the cone over P has dimension 1 more than the dimension of P. What I'd like to deduce now is a reciprocity theorem on the level of Ehrhart polynomials or Ehrhart quasi-polynomials. And this turns out to be not exactly straightforward. It's not deep, but there's now some steps necessary on the level of generating functions. In the book, this is being done through a series of exercises, but let me tell you sort of the philosophy behind this. So in the following situation where we have some function f of n, and let's assume this is a polynomial. Or quasi-polynomial, then you know if we now form the generating function, so what I call capital F over here, this will be a rational function. Okay, at the same time, so this is sort of the reciprocal side. If I look at the function f of negative n, again, this will be a polynomial. So let me form this generating function that I call f circle. So now what I do is I plug in negative evaluations of my polynomial. Well, this is also a polynomial. So again, this generating function that you see on the right over here will evaluate to a rational function. You can think of both generating functions f and f circle as encoding the evaluations over all integers. On one side, you have the positive integers. On the other side, you have negative integers. And we're going to include 0 somewhere. Let's say we'll include them like here on the positive side. At any rate, I claim as rational functions, I have a relation now. I will stress the same thing as I've stressed with Stanley's theorem in both versions that we've seen. On the level of generating functions, what I just put in a green box actually does not make sense, but I invite you to realize that on the level of rational functions, this is a valid identity. If you now bring this identity back into the picture of Ehrhart series and translate the reciprocity theorem you see up here, theorem 4.4, in the language given by this general setup of rational generating functions for polynomials or for quasi-polynomials, you get the Ehrhart-Macdonald reciprocity theorem. So this is now a reciprocity theorem on the level of the original counting functions, either Ehrhart polynomials or Ehrhart quasi-polynomials. Yeah, so I think of this theorem 4.1 here as really a corollary of theorem 4.4, and in fact you could have started either way. So they're really sort of equivalent formulations of the same theorem. Let me make one last comment about theorem 4.1 here. Just like Stanley reciprocity and theorem 4.4, the reciprocity theorem for Ehrhart series, only makes sense in the world of rational functions. Theorem 4.1 only makes sense in the world of polynomials or quasi-polynomials. So one way to rephrase Ehrhart-Macdonald reciprocity is to say, I have the quasi-polynomial that computes integer points in dilates of a polytope, and I have a quasi-polynomial that computes integer points in dilates of the interior of the polytope. And these two quasi-polynomials have a functional relation. And it's the relation given by this identity.